Alright, guys. So we'll be taking some examples on the Frobenius method. The Frobenius method is also known as the indician root. So when we divide through by the coefficient of the second derivative, we have the expression given there. So to have our regular point, we put the denominator of y to 0. So we'll be having x to be equals to 0 as a regular point, and also um s equals to minus 1 to be a regular point, that is singular regular point. All right, so that's it. Now, for us to solve using Frobenius method, we let our y be equals to the sum of a's of r x raised to power r plus c, and the first derivative, second derivative are written there respectively. All right, so we insert our values back. We have 2x squared plus 2x to the sum of all that r plus c minus 1 is of r plus x of r plus c. So we inserted everything. So at the end of the day, you see we substitute r equals to 0 to all the sum. And why are we doing that? The reason why we are substituting r equals to 0 is to linearize everything. So that is, you see, we are having s raised to power r plus c minus 2 in some summation, while we have r plus c minus 1 in summation. So you substitute x raised to power r plus c, r equals to 0 to all the sum. So on substituting, we have so after substituting, you see that when we substitute r equals to 0 in the series that has a's of r s raised to power r plus c minus 1, you see we'll be having the first one. We have 2c open bracket c minus 1 a's of naught x raised to power c minus 1. Then after inserting r equals to 0, the next series, since it is a series, we have the sum of 1. After inserting 0, we have 1. Assuming we've applied equals to 1, you continue from equals to 2. Then we move to the second one. You insert r equals to 0. Then you have 3c a naught s raised to power c minus 1. So that is that. So just take a look at that. So substituting r equals to 0 to all the summand with s raised to power r plus c. All right, so now linear, I said earlier the reason why we are inserting r equals to 0 was to linearize. Now for more linearization, we'll set r equals to r plus 1 to all the summand again with s raised to power r plus c minus 1. So now you can see all the series, all the terms as s raised to power r plus c, all of them as s raised to power r plus c, but we have to put r equals to r plus 1. So inserting r equals to r plus 1, this simply means that the sum that was having r equals to 1 before will now turn to 0. The sum that was having r equals to 1 before will now turn to 0, because r minus 1 minus 1 equals 0. You understand? So everything, we are now balanced. Therefore, bringing out the constant term, we have 2c minus 1 is of naught s raised to power c minus 1 plus 3c a naught s raised to power c minus 1. So just you can easily write it out there. I forgot to put it there. Then we bring all the summation signs together. So we have 2r plus c plus 1, r plus c plus 3r plus c plus 1. Then we factorize. So after this point, we factorize out the like terms. Now on factorizing, we factorize out the constant term. Then we have 2c c minus 1 and all that. Then bringing it down, we factorize out c. So if we factorize out c, we have 2c minus 1 plus 3 is of naught x raised to power c minus 1, factorizing that out to 2. So when we open the bracket, 2c minus 2 plus 3, we have 2c plus 1c. Then we equate c to 0 and we have c equals to minus 1 over 2. Note that a of naught is not equals to 0. That's our indician root. So c 0 and c minus 1 over 2, they are our indician roots. So when c is equals to 0, we insert it back to the sum of r plus c, 2r plus 3 is of r plus 1 plus r 2r plus 1 minus 1 is of r equals to 0. When c equals to 0, that will be our new expression from the first line. From the first line, when c is equals to 0, you see, from the first line we have sum of r plus c plus 1 open bracket 2r plus c plus 3. Now when our c becomes 0, we have r plus c 2r plus 3 is of r plus 1. So making is of r plus 1 the subject of the formula, we have our recursive sequence there. So that is that for our recursive sequence. So when r equals to 0, we insert r equals to 0 in the recursive sequence. Then you have a of 1 to be a naught over 1 over 3, 1 times 3. Then when r equals to 1, we have minus 2 over 2.5, 2 times 5a1, but a1 is a naught over 1.3. Then we have that to be minus a naught over 1.1 times 3 times 5. So respectively for r equals to 2, we have our a's of 3 to be equals to 0, to be equals to a over 2, to be equals to 1 over 7 times 5 is of naught. Now since there is an alternating sign, we have our general a of 2k will be minus 1. You notice the first sign is positive, the second sign is negative, the third sign is positive. So you have minus 1 raised to power k plus 1 is of naught over 2k minus 1 times 2k plus 1. The essence of 2k minus 1 and 2k plus 1 is to determine the general term for the denominators. 2k minus 1, when it is equals to 0, when r equals to 0 is 1. 2k plus 1, when r equals to 0 is 3. So the same thing goes for the rest. So we have our general formula to be that y prime of c equals to 0 to be that. Now for when c equals to minus 1 over 2, we put minus 1 over 2 with replace to c. Then we have our new recursive sequence to be that. So we put when r equals to 0, you see we have our value there, r equals to 1, r equals to 2, r equals to 3, and we have a1, a2, a3, and a4 respectively. Then to have our general solution, we add the first value, our first solution when c equals to 0 plus our second solution when c equals to 1 over 2 to arrive at our general solution. So our general solution is given as k1. You can represent it as a, you can represent it as k1, you can also represent it as any alphabet of your choice. So that is that for this video. And meanwhile, take a look at the expression. To write the general expression, you have to recall that y is equals to the sum of a's of n s raised to power k. So that is the general expression. So we start from a's of naught plus a's of 1 plus a2 plus a3, like that. So that is that for this video. Thank you.